I just spent 1 month making a game as fast as possible. Now, this was supposed to be a 2-day challenge, and if you tally up all the days I actually worked on it, it works out to be like a 5-day challenge, but that's besides the point. The idea was to have a dodgeball game played on the ocean, and players would shoot and try to knock each other off of the field. Now, this was an interesting project for me, and sort of a proof of concept as well, as I plan to make a multiplayer game. Secondly, it just feels good to finish something, and I just wanted to prove to myself that I could finish something. So let's get into it. Unity is the game engine we're using, and I have like 4 years of experience with it. Unity ships their own multiplayer networking solutions, and there is stuff like Photon out there, but I feel like this is bringing all this unnecessary complexity with it. I just wanted something simpler for my needs. First, I started on the core mechanics. The ships need to move around and shoot cannons. I have a cool water system asset from the store. Crest Ocean System is awesome, and you should totally check it out if you have a game that incorporates water. Hashtag not sponsored. I had to remember how to use it, but once I remembered how it worked, we were off to the races. I had this cool idea that the cannons could be able to shoot cannonballs and curves so that you could hook shot someone off of the map. So we'll need to implement a sine wave function into the game so that the ball is instantiated at the beginning of the curve and is destroyed at the end of the curve. Now that we have a playable ship character, we can get into networking. Now, this was a learning experience for me. I sort of knew about network protocols and the game engine Netcode, but I've never really had to do any sort of applied learning, so this was all new for me. Now, I really wish I had done more research here before I just jumped in and started, but it is what it is. I decided on a host to server to clients architecture because I thought having a server that is also running its own bespoke version of the game would just be too complicated. So the server here is more of a relay than anything else. Now we need to get data to the server, which means that we need some way to send messages to the server, and I had some ideas about this before I jumped in. For one, I knew that I wanted to use TCP based on John Carmack's comments about TCP versus UDP on the Lex Friedman podcast.
About the networking stuff, because it's interesting where I learned these things by reading books. So I would get a book on networking, find something, I read all about it and learn, okay, packets, they can be, out of order, lost, or duplicated. These are all the things that can theoretically happen to packets. So I wind up spending all this time thinking about how do we deal about all of that. And it turns out, of course, in the real world, those are things that, yes, theoretically can happen with multiple routes, but they really aren't things that your 99.999% of your packets have to deal with. So there was learning experiences about lots of that, and why when TCP is appropriate versus UDP, and how if you do things in UDP, you wind up reinventing TCP badly in almost all cases. So there's good arguments for using both for different game technology, different parts of the game process, transitioning from level to level and all.
As for messaging, the actual data that is sent and received by sockets, for that we're going with flat buffers. I considered using JSON, but I landed on flat buffers because you can keep your type safety and you have a pretty good idea if your data is there or not. Also, it is way more efficient to send flat buffers over the network because they are basically just bytes of memory that you yeet to the server. And because we're using TCP, which is slower, having a huge text payload on each message isn't ideal. Now let's take a peek at the server code. The server goes into listening mode and it's on the clients to reach out and send the first message.
Hello. You'll have to speak up, I'm wearing a towel.
So when a server sends a message, it needs to handshake with the server. I'm mainly just doing this as a security measure to make sure that the server isn't trying to read any traffic that wasn't sent by one of my clients. If this was a real project, we could use OAuth or something like that to make this more secure, but I think this should be fine for our tiny non-commercial project. After a client handshakes, every message after that is of type update message. So each incoming message has a prefix of 4 bytes. The prefix is just an unsigned 32-bit integer that holds the total size of the entire message, not including the prefix. So basically, we parse the first 4 bytes, and then we know if we should keep listening for more data to come over the network, or if we can parse the message into a generated flat buffer message class. We need to pause here to talk about Big Endian and Little Endian. Endianness, or byte order, describes how computers organize the bytes that make up numbers. Depending on your computer's processor, it'll either arrange bytes with the least significant byte at the lowest memory address, Little Endian, or it'll arrange bytes with the most significant values at the lowest memory address, big Indian. So you'll notice that I bit shift the prefix of our message so that it is always big Indian. The reason for this is that conventionally, network messages are always big Indian. This kind of doesn't really matter because we all use ARM or x86 CPUs these days, which are both little Indian anyway. So this whole converting it to big Indian to move it across the network only to convert it back to little Indian is a little bit nonsense, but we're trying to do things the right way here, okay guys? So all of that said, Indianness on processors has not always been nailed down. So like, for example, PowerPC was a big Indian CPU. So if you make a video game that gets played for decades and the popular CPU architecture later on is a different Indianness on the client than the server, you could have a problem, and that might not be easy to debug and figure out later on down the road. So we've received a message. Now we need to know, hey, did this come from the client or the host? The way that our relay is going to work is that we have an authoritative host.
What do you mean by that?
That means that if you're a client, you only send keystrokes and mouse movement to the server, which gets relayed to the host. If you're the host, you only send the state of the game back to the clients. So if it's a host, we need to save all the new positions of our networked game objects in our game, and we need to get a list of the latest client inputs and send that back to the host. If the message sent to the server is from a client, on the other hand, this process is exactly the opposite. You just save your keystrokes to the list of all the client's keystrokes, and you reply to the client with all of the latest positions from the server. Do you see anything wrong with this approach? It took me a few days to figure this out. Every time a client or a host comes to the server overwrites the previous message that was sent. This is good from the standpoint that you only want the latest data. But this is bad if the previous message said, hey, delete some stuff. Well, you don't freaking have that anymore. Now, this was like 2 days ago that I figured this out, and I realized that the right way to do this would be to have a buffer of update messages like they do in Valorant, and to have fake interpolated updates in between each real update to help with the smoothness. Now, I sort of chose to band-aid this because I felt like I was almost done with this project, and in order to implement this the right way would probably have me rewriting all of the client-side and server-side netcode to handle a list of updates rather than just one. So I decided it would just be easier to have clients rationalize whether an object should be alive given what it knows. So for example, because updates were getting skipped, I would have cannonballs like hang in midair rather than getting destroyed because the update that was supposed to tell the client to destroy them got overwritten by the host before the client got it. So now the cannonballs are destroyed every 2 seconds on the host and every 10 seconds on the client, and that mostly works. Now let's take a look at the desktop game piece of this. Again, we have to distinguish between the host and the clients, and for the most part the code is what you would expect. You keep a list of network game objects, and when the host receives input, it moves all the networked objects and relays those to new positions to the clients. Clients do the exact opposite. They take their inputs and they receive new positions for everything. Clients also have this workaround in the code where between updates, they sort of interpolate between the last known position and the next position, which is better than doing nothing, but not as good as the Valorant solution I talked about earlier. And that's basically it. You can watch me and my wife play the game. I appreciate you guys watching the video. And
Has it always been 5 minutes long?
yeah. There's like no wall anymore, so you can just like run up on me now.
Okay.
Oh shit. Oh my god. It's like really shaky for me.
Where are you shooting at?
I'm trying to turn around. Oh man. I don't even know how this gonna. Like flying to The water in the clouds look dope.
Where are you?
I'm behind you, I think. We both need to turn around. I keep trying to. The more times you hit somebody, the higher their percent goes up, like some Super Smash Bros, and the more likely they are to fly off the map. So you actually do more more hit damage. Okay. Do you need to go check on that?
Yeah, I need to.
You get a point first?
I got a lot of points, yeah. I win. Game over. I got 6 points. You have 1 somehow.